It was 2:37 a.m., and the air inside the shop shimmered like a furnace. Sparks stitched brief stars across the dark. A rivet gun shattered like a machine that would not sleep. In the heartbeat between hammer strikes and a lathe's steady song, men and women leaned close to hot metal as if to listen for its answer. This is the building the title points to, a plant that, in our telling, became a war machine in miniature, a place where the P-47 Thunderbolt, a piston-powered titan of the skies, was assembled and tuned until it could be trusted. The title says it was built under constant bombing. That phrase will be treated here as a dramatized composite. Some plants did endure repeated raids. Many lived with the perpetual threat of air attack. And every factory worked under the pressure of targets, alarms, and the knowledge that each hour lost could cost men in the air. What you are about to hear stitches together those textures, the heat, the failure, the small salvations that defined wartime production. The factory smelled of oil and hot metal, of sweat and coffee breathed through steel-toed boots. It moved like an organism. Conveyor belts were spinal columns, cranes, ribs, the test cells, a throat that coughed out flame and a sound like a beast clearing its lungs. When a crankshaft failed or a casting cracked, the building shuddered as if it had been struck. When an acceptance test ran clean for an hour, the relief fell through the shop like rain. Why the P-47 mattered? Quickly, plainly, without myth. The Thunderbolt was built to be a bulletproof escort and an angry, heavy fighter bomber. With its rugged airframe, high speed and dive, and heavy armament, it could meet enemy fighters and then turn to hammer ground targets. It could take punishment and keep coming back. For commanders planning sorties over Europe and the Pacific, an aircraft that could climb fast, deliver ordnance, and keep a pilot alive even after being shot through, that was not optional. That was a link between the factory floor and a bomber pilot still hoping to return. But the plane itself was only as certain as its heart. The engine, the gearbox, the complicated plumbing of superchargers and exhausts and mounts that translated metal into flight. On paper, designs read like elegant math. On the inside of a shop at 3 a.m., designs met grit and human limits. Production at scale introduced problems that prototypes had never known. The same casting that behaved in a test rig would explode when flooded with noise and vibration on an assembly line. A heat treatment that worked on a small batch would produce porosity when poured by the thousands. The men and women who learned to read these failures, foremen, metallurgists, machine operators, draftsmen, became, in effect, the engineers of scale. They took the blueprints as a starting prayer and then argued with metal until it yielded. A foreman named Walter Hargreaves, composite, part mentor and part mechanic, walked the line with a rule as simple as it was sacred. Listen first, hurry second. Walter had the habit of standing with his palm flat on a cylinder head while it cooled. He would close his eyes and speak to the metal the way a doctor might listen to a chest. "It's telling me," he would say to no one and everyone, "where it holds and where it will break." Around Walter moved a cast of voices. Miguel Ortega, 19, a night shift apprentice whose father had been a machinist before the war. He kept a copy of the aircraft manual in his locker and would trace diagrams with a grease-stained finger during stolen moments. "If that turbo coughed again like last week, I thought I'd throw up," he'd write later in a cramped line in a notebook that smelled of oil and cigarettes. Sam Keene, a fitter with a battered knuckle and the conscientiousness of a draftsman, had returned from a hospital bed to the bench before a full year had passed. His smile had a quickness that veered toward defensiveness. Eddie Hugh, the draftsman, who could see a stress line before it became a fracture, kept his sketches coffee-stained and close to his chest. These were not celebrities of engineering. They were the people who translated drawings into reality every hour of every night shift. Their work was iterative and sometimes tender. Their victories often registered as a dozen small fixes that kept a crankcase from growing a hairline fracture or stopped a cooling jacket from collapsing under pressure. Outside, the threat of air raids intersected with bureaucracy. Procurement offices in Washington and the higher echelons of the Army Air Forces pushed for numbers, more sorties, more readiness, faster acceptance runs. Official dispatches were formal and cold. Increase output by 40% in 90 days. Men like Walter read that paper and felt the human arithmetic behind the numbers. Each plane not shipped was a squadron that might not fly. General names were whispered on the shop floor, General Arnold, as an emblem of pressure and expectation, less as a demand. The technical problems were stubborn and, crucially, social. A failed casting could be traced back to the foundry floor where a sand mold had been contaminated, but it could also be traced to a change in the alloy caused by an interrupted supply line. A crack in a gear transmitted vibration into other parts, and that vibration moved like wildfire down the assembly line, causing small, unpredictable failures in seemingly unrelated places. The fix, when it came, had to be as systemic as the failure, not merely replacing a part, but altering a process. In the early days, a typical failure cycle played out like a ritual. An acceptance test would begin in a test cell, an armored room with a window like a porthole, gauges flaring like watchful eyes. The engine would be cranked, warmed, then pulled to speed. For a few seconds, things could look magnificent. Oil pressure steady, temperature climbing in a predictable curve, vibrations minimal. Then, with no heroism in the physics, a harmonic would emerge. A specific RPM where the whole assembly sang as one. If the song was right, it remained a hum. If not, the song became a scream. When the scream came, it often began with a noise so small that men would shrug and keep turning wrenches. A hairline crack in a casting would spread under alternating stress, tensile, compressive, torsional, until it liberated a piece. The liberated piece would strike another component. Oil lines would shear, bearings would fry. A test cell would go from controlled roar to a geyser of expelled oil and a blue glare as metal met air. In the worst cases, a casting would simply explode outward, sending shrapnel of metal into the heavy concrete. Those moments left a silence after the alarm stopped, a silence heavy with the idea that luck had run its course, and that someone, somewhere, would have to account for that missing hour and that damaged life. Walter learned to read those silences. A broken crank isn't just a bit of scrap, he'd tell his crew. It's a question. Where did we change the way we pour? Where did we change the heat? Where did we change the rhythm of the line? The answer rarely came from a solitary genius. It arrived because somebody, sometimes a woman on the line with a set of small, patient hands, noticed a reoccurrence of porosity at the same flange. Sometimes it was an apprentice who, after a week of watching, saw that the rinse water on a casting ran in a particular way and could carry a contaminant into the mold. And sometimes it was a mechanic who, having survived an explosion, insisted the test procedure include an extra monitoring gauge. These were the iterative victories that no ledger could capture. Night after night, the test cells were the shop's Qibla. Men and women gathered around viewing ports to watch numbers climb on a bank of instruments. A single, sustained run, 6 hours, 12, was proof against the rumor that a given part was unreliable. When a run held, they drank coffee like celebrants. When a run failed, the men and women left with the sensation of being reprimanded by the metal itself. Many failures were rooted in the unavoidable discrepancy between laboratory and mass production. In a lab, an engineer might verify a heat treatment on a single crankcase and measure hardness across multiple points with a probe. On the production floor, heat-treating ovens held hundreds of pieces at once. The loading patterns and the uneven circulation of air changed results in ways that a theoretical calculation had not foreseen. A furnace that looked identical could hold pockets where temperature deviated by tens of degrees. Those differences were enough to change grain structures in steel, and grain structure was the memory of a metal's behavior under stress. Metallurgy was sometimes described on the floor as a kind of poetry, the way heat could coax a metal to a state where it would bend, not break, where it would absorb a hit and then be forgiving. But the language of poetry hid hard cash, lost minutes, and risked lives. A failed prop plate could be the beginning of a chain whose end was a wrecked aircraft. Hearing about the failures was one thing, seeing their consequences was another. Miguel recalled, in a half-line of a diary, the evening a test stand ducked into chaos. We watched a cylinder head split like bread. He described the sight in clinical, boyish terms, the way pieces of metal flew, the smell of burnt oil, the way the windows of the viewing port fogged with the heat. Later, in a letter home, he would choose to paper over the fear with humor. "Tell Ma I've graduated from student to scarecrow." But the immediate record showed how close production and catastrophe sat on the shop floor. The human cost presented itself in quieter ways as well. The nurse's station that stitched up knuckles and knees, the list of compound fractures in a ledger too formal to mention names, the extra chemotherapy of exhaustion that came from double shifts. There were other violences as well. The moral cost of knowing that what you made would be used to break things, sometimes houses, sometimes lives. The shop floor handled this by folding it into routine. There were jokes told along the line and small acts of tenderness. Someone slipping a letter home, someone buying an extra loaf for a tired partner. The pressure from above made those small human economies more brittle. When the procurement office demanded more units in less time, shortcuts whispered temptations. A foreman with integrity might hold the line and refuse to sign off on a suspect casing. Another, under fire from supervisors and budget committees, might press the test bench to meet quota. The result was a moral calculus played out in terms of torque and tolerances. Engineers who were accustomed to designing in peace were suddenly designers in a crucible. They learned to value processes that were tolerant of variation. The language changed. Instead of seeking the perfect microstructure, they sought the process that would produce acceptable microstructures across 1,000 parts. That meant changes in how molds were gated, in how vents were cut, in the timing of quenches, and in the organization of assembly. One recurring technical enemy was vibration. Engines, when powered, are orchestrations of forces, counterweight spinning, valves opening and closing, pistons accelerating and decelerating a few dozen times per second. Each component introduced its own frequency into the system, and when two frequencies coupled in a single assembly, they could amplify until metal failed. The shop floor had its own vocabulary for this: the event, the settle, the runout. The engineers measured it with dial indicators and stroboscopes, but understanding it required empathy, the ability to feel when an assembly was unhappy. To address vibration, the shop's engineers tried everything within practical limits. They redesigned engine mounts to isolate frequencies. They adjusted the lengths of shafts. They experimented with damping materials, inserts that would absorb amplitude instead of letting it travel. Some experiments were obvious: change the mounting flange, relocate a support. Others were small and counterintuitive and required patience. Add a fillet here to reduce stress concentration. Change the radius at a corner so fatigue would not begin as readily. Each small change had ripple effects. At a bench where bearings were fitted, a woman named Ruth, short and nimble-fingered, found that a particular bearing alloy tended to scuff when torque curves shifted. She proposed a different finish on the bearing journal and persuaded the engineering office to let her try it. Her fix worked in small batches. When scaled, unexpected new problems appeared. The new finish demanded a different lubricant behavior in cold weather. Ruth and the lubricant chemist argued for 3 nights over cups of instant coffee until they settled on a lubricant additive that maintained a film even at lower temperatures. This anecdote captures the broader truth.
A single item's reliability hinged on dozens of small decisions, many of which involved people with names and habits, not anonymous directives. The production of the P-47 in large quantities required this network of human intelligence to stitch itself into a system that could absorb errors and still produce aircraft that returned to combat. The factory's physical expansion mirrored this. Assembly lines grew like city avenues. Subassemblies were sent down conveyor belts to be bolted into place. Scaffolds rose where engineers needed access to complex plumbing. Women who had been encouraged into industrial labor by necessity kept rivet guns singing. Their work was often faster and more consistent than their male counterparts, and shop leaders noticed. The lines operated in overlapping shifts to ensure that the plant never truly slept. Yet more workers did not mean fewer failures. The complexity of logistics, metal supply chains, heat treat cycles, machining tolerances, multiplied with scale. A delayed shipment of chromium changed the properties of dozens of components. An overloaded oven caused a stray run-out of temper. Scale demanded process engineering, detailed charts of timing, inspection points with sample sizes determined by statistical tables, and X-ray inspections of critical castings to detect porosity. The X-ray bay became a solemn checkpoint. A casting that showed a bubble in a critical load-bearing area was quarantined and studied.
Sometimes the repair was simple. Rework the gating, melt again, recast. Other times, the scrap bin filled with thousands of dollars worth of iron that could not be salvaged. At a moment when the war demanded more aircraft than one could reasonably produce, the sight of a scrap bin was both a cost and a moral question. In the shop, small rituals kept morale afloat. Coffee pots were tended like beacons. Someone always carried a radio tuned to the same station. Workers would listen to news of the front between tasks. Birthdays were celebrated in the break room with a contraband cake. These rituals were exercises in insistence that life, in some form, persist inside an institution devoted to instruments of war. Letters and diaries give us the human texture of those nights. One mechanic, scratched across a cramped notebook, wrote after a long run, "The engine settled like a beast that had been stroke-fed. We all felt it, like a prayer answered." Another, who had lost a brother in a bombing raid overseas, wrote with a more conflicted hand, "I tuned them to kill, and then I fix them when they break. Sometimes I think I am tuning only my own grief." The rhythm of failure and repair escalated when the factory came under external duress. Air raid sirens, whether actual or rumored, changed the psychology inside the plant. Men and women learned to lay down tools in the middle of a task and move to shelter in an orderly way. Sometimes the alarms were false, and some days were quiet. Sometimes they were not. Even when raids did not strike the plant directly, the presence of exploding flares on the horizon and the distant rumble of anti-aircraft guns made the work feel urgent in a new, existential way. This environment shaped decision-making. Safety margins were insisted on not merely as engineering prudence, but as a way to reduce the cost of loss in human lives. A bolted bracket that could shear at 2.5 Gs might be acceptable in theory. In practice, engineers aimed for 4 or 5 Gs if it meant a pilot had a chance to nurse a damaged aircraft home. Those decisions had resource consequences: more alloy saved, more machining time taken. But they also carried a moral weight that no accounting system could quantify. Pressure from above intersected with the shop's internal politics in decisive moments. Inspectors from the Procurement Bureau visited with clipboards and questions. A clean acceptance test would be rewarded with more contracts and fewer inspections. A failure might invite a day of grinding, of rework, and second-guessing. The men and women on the floor learned to prepare for those visits. They polished the visible parts and hid the mess behind partitions. They rehearsed explanations for anomalies. The theater of inspection was a performance that hid a tremendous amount of improvisation. Amid all this, a peculiar culture of secrecy and humility arose. Engineers who proposed major changes, redesigning a mount, altering a cooling passage, had to provide evidence, sometimes in the form of test runs, sometimes in the form of a sketch, and the kind of conviction that made others willing to try. Authority on the line was as often won by small, demonstrable wins as it was assigned by rank. One of the most persistent problems that rose again and again was cooling under sustained high-power runs. The P-47's engine, an R-2800 class radial, relied on air cooling augmented by carefully routed oil and exhaust arrangements. In lab conditions, cooling curves looked neat. In field conditions, aircraft with marginal cooling would lace the air with smoke. On the ground, on the test stand, the challenge was to model in miniature the heat soak that would occur in a long climb or heavy combat turn. Engineers experimented with ducting, baffling, and oil flow rate adjustments. Some fixes were surprisingly low-tech. A slight change in the angle of a baffle, a different packing material sealing the joint so airflow was less turbulent. Others demanded careful study of how heat traveled through bulkheads and how much oil could be kept in circulation before viscosity changed uncomfortably. The shop fought as much with the invisible as with the visible. Heat, vibration, and metallurgical microstructure are not photogenic. They are the quiet enemies of reliability. The people who mastered them did so by making peace with the idea that certainty was probabilistic. One could not state that a part would never fail. One could only reduce the chance of failure to a tolerable level, and then watch, test, and refine. The narrative arc across those early months is one of ratcheting pressure and incremental gain. Each small success nudged production upward. Each failure demanded a plunge into the details. The need for planes was urgent, the margin for error thin, and the human cost under the surface. The plant's rhythm and the lives within it magnified under the glare of a particular month when procurement sent a directive: accelerate the production schedule by stacking more acceptance runs within each week. The test cell schedule doubled. Men who had been working nights were reassigned to daytime shifts in a way that hollowed out what little rest they had. The morale that had been a held thing, slowly nurtured, began to show stress. It was in this pressure cooker that an episode occurred which would later be recounted most nights at the bar. An acceptance run that began as one of many, and then, within 90 minutes, became the axis of everything. The engine, warmed and buffed, had made it past the first hour. The crew gathered at the viewing port, the way congregations gather for a rite. A small cluster of engineers watched the vibration meter like a flock watches a weather vane. The numbers were steady, then a slight uptick. One of the dials crept off its plateau. Would it hold? Someone asked, as much a question to the room as to the machine. A line of narrative choices followed. The easiest would have been to call it and pull the engine for inspection. That would cost time and risk missing the target quotas. The other choice, push the run an extra 15 minutes. Engineers weighed the statistical likelihoods, the human cost, another night of digging deeper into the problem, and what they knew of the mandates that had come down from above. The decision landed in the hands of a small, informal committee: the foreman Walter, the chief test technician, and a senior metallurgist who had the habit of resting a hand on the instrument panel when he was anxious. They chose to push. The run continued. Around the viewing port, faces were taut. Inside the cell, the engine whispered and then grew louder, as if taking in breath. Vibrations rose infinitesimally, then settled. The clock went past a milestone, 2 hours, then 3. A cheer held low, like men who had learned that celebration could be dangerous in case it angered fate. If success in testing is a kind of baptism, this was one. The engine, assembled from 1,000 decisions, many of them small, ran not perfectly, but within acceptable bounds, for a duration that meant it could be trusted on a sortie. The shop's morale shifted. The ledger of doubt had a new entry: this assembly could make it through the expected loads. That night, the victory was modest and human.
Men hugged like boys. Miguel wrote in a hurried note, "We made a thing that keeps on running. It felt like learning to breathe again." Sam, whose knuckles still throbbed from a late repair, went home and slept for 12 hours. But this episodic success also carried a secret. It was fragile. The parameters had been nudged, processes adjusted slightly, and the device had been moved into a narrow safe zone that had to be replicated 1,000 times to mean anything for the war. The factory had proven one assembly. It had not yet proven scale. As part 1 of this account moves forward, the stakes will rise and the methods will deepen. The shop floor will face more tests, more explosions, more quiet triumphs. Engineers will try experiments that are small enough to be done overnight, but consequential enough to alter the course of production. Men and women will come back from the hospital and stand at the lathe as if to defy the possibility that their work was a form of gambling with lives. And outside the shops, the war will continue to place every hour of manufacturing under pressure. For now, the plant holds a fragile hope. An engine that once screamed is humming. An acceptance run has passed. A crew has tasted what success feels like on a good night. The building breathes, the cranes creak, and the rivet guns take up their steady staccato again.
The road to mass production is long and paved with setbacks, but in the dim glow of the test cell's instruments and the soft light over the assembly line, there is a sense that a turning point may be near. If you like this kind of deep dive into hidden WWII stories, subscribe. They set to work in the new week with that cautious confidence. Process documents were rewritten, inspection points added. The foundry manager instructed the pattern shop to alter gating on specific castings. The engineering team formalized what had been ad hoc solutions, a preheat cup, a pause in the quench schedule, a change in the torque sequence for attaching the accessory gearbox. Little charts began to appear taped to the machine frames, the kind that reduce knowledge to a sequence and thus protect precious know-how from being lost in the shuffle. Not everything responded. The redesigned mounting worked better for one engine family, but meant a longer machine cycle for another. A chosen lubricant that performed admirably at the test stand thickened in cold mornings during a late autumn week, causing sticky starts and a set of new headaches. The supply chain, stretched already thin by wartime demand, offered substitutions, sometimes equivalent, sometimes not. And the shop learned to treat any change of supplier as a potential change in part behavior. Here, the engineers began to lean into a different mode, the art of toleration. They designed assemblies that would not be brittle to small changes, that could accept a variance of plus or minus a degree in tempering without shedding reliability. The work was less about perfection and more about resilience. How to design systems that would degrade gracefully instead of catastrophically. That led to changes in inspection philosophy. Instead of inspecting only at the end of a process, the shop instituted in-process inspections, measuring at intermediate steps to detect trends rather than merely outcomes. They installed more gauges, and the test stands were given automated data loggers. What had once been guessed from a listening post became data that could be plotted and interrogated. The data told stories. Patterns emerged. When the foundry had a certain shift in its casting schedule, porosity incidents rose by a measurable fraction. When the oven loads exceeded a certain threshold, the variance in hardness increased. These correlations allowed engineers to pinpoint where process discipline could arrest a failure before it occurred. Yet, for all the progress, the human narratives remained the central force. A drill press operator who had adapted a makeshift jig on his own saved an assembly from misalignment for a full week before his supervisor noticed. A draftsman who spent his off hours sketching a gentler fillet radius earned the engineering group's trust after a prototype passed a grueling run. Their stories threaded the technical narrative with a clear human line. Ingenuity lived in the small, practiced improvisations of those who did the work every hour. And the tension never left. The presence of aerial threat, the push from procurement, the knowledge that every delay had consequences in lives made every decision feel weighty. When alarms wailed that week in the local town, anti-aircraft artillery lighting the night into false daylight, men paused over wrenches and wondered, not for the first time, what the arithmetic of their hours would mean to someone in a bomber over Germany or a fighter pilot's life over a Pacific island. At the junction where Part 1 pauses, the factory is no longer the chaotic room of early failure. It is a place of engaged systems, of process charts and altered machining sequences, of a test cell with a recent success under its belt. But it is not yet a production engine that has run flawlessly 1,000 times. The challenge remains to scale wins into reliable throughput, to make the conditions that produced one clean run reproducible across shifts, suppliers, and months. The next decisions were about scale. Which processes could be trusted to scale without introducing a new class of failure? Which needed rethinking from the ground up? Men like Walter and technicians like Ruth and Miguel would be asked to take their small victories and teach them to an army of new hands. Night fell on the shop again. The shadows pooled under benches. A test cell hummed somewhere down the corridor. In the quiet, a small group of workers bent over a bench to study a new baffle design. Outside, flares from anti-aircraft guns tossed their light across distant clouds. Inside the building, a team prepared to run an engine, a full assembly, longer than it had ever gone. They tightened every bolt, checked every gauge, and listened. The moment before the run was a small, thin thing. It was the space where hope and dread meet. The men and women who had already survived explosions and near misses knew how brittle success could be. They also knew with stubborn clarity why they tried. Because a plane that returned kept alive stories that could still be told. They closed the hatch. The engine turned over. Instruments flickered. Outside, the town slept under a round of distant anti-aircraft fire. Inside, the shop held its breath. The starter caught, the engine found its rhythm, and the viewing port glass fogged with the heat of a machine that had earned another hour. The meters climbed in patient arcs. A small, almost ashamed cheer moved along the line like a ripple on water, careful, as if too loud a sound might wake whatever, somewhere, still slept uneasily. They logged every nuance. The data recorder hummed. A clerk in a pale apron circled figures on a sheet with a fountain pen, folding the numbers into a tidy story others could read. Walter kept his palm on the panel for a long time, feeling the instrument boards wake the way sailors feel the roll of a ship. When the run passed a prearranged milestone without the tremor that had haunted them, he lifted his hand and let out a breath he had not known he held. The relief did not explode into raucous triumph. It skimmed the shop and settled into the small rituals of the night. More coffee, a handshake, a return smile. That run was proof that a single assembly, built with care and guided by ad hoc fixes, could behave the way the drawings intended. It was not a guarantee, it was a promise inked in the ledger of attempts. To make that promise mean anything across hundreds of aircraft would demand patient reproduction, and patient reproduction would obey its own logic of trouble. In the following weeks, the factory watched itself teach other hands to do the things it had learned. Templates were copied, jigs were standardized, and the language of adjustments. Add a bead of sealant here, stagger the quench times by minutes, moved from Walter's mouth into a binder, then onto laminated cards clipped to machines. The apprenticeship program deepened. Older machinists were paired with younger recruits, and rookie mistakes were no longer tolerated casually. A wrong torque could ripple into a failure days later in flight. The cost was not only the scrap and overtime, but the possibility of a return note from the front that began, curtly, with the word lost. Scale introduced new enemies. Where a single mechanic could cradle a crankcase and notice a subtle misalignment, the conveyorized line demanded jigs that would hold tolerances without a human eye coaxing them. The more they mechanized the work of alignment, the more they risked a systemic error being repeated 100-fold. Once, a seemingly blameless fixture, an alignment block worn a few thousandths of an inch, translated into a whole run of assemblies with a slight misread on final clearance. The failure did not appear in the first hour of a test. It bloomed under months of service as fatigue. The cost, measured later in rework and replacements, was the price of a tolerance that lost its context. Supply lines, too, were a theater of uncertainty. A batch of alloy arrived with a slightly different composition. The foundrymen, pressed for time, mixed it according to the usual ratios and hoped their empirical feel would bridge the gap. Sometimes it did. Sometimes a subtle shift in silicon or manganese content altered grain flow and made a casting susceptible to hot tearing. A ferryman of logistics would bring the news. An inbound shipment delayed by a rail strike, an alternate chrome source whose metal behaved like a stranger. Each change required a revalidation of assumptions. And overhead, always overhead, there was the threat of the sky. The plant was not under siege in a way that could be labeled historically for every hour of every day. This telling has already marked itself as a composite of many factories' experiences. Still, alarms were reality for the workers. On certain nights, the siren's cry was close and shattering. Flares streaked, and the horizon washed red with incendiary arcs. Sometimes, the plant took shelter drills as if rehearsing for an event that might never occur. Sometimes the alarms were false. Sometimes, on a wet night near the docks, the plant did take damage from bombs that fell within the industrial triangle of the region. Shattered panes, scorched asphalt, and a temporary stoppage in a rail spur that fed the foundry. Even where direct hits did not strike the plant, the psychology of being a target hardened decisions. Redundancy became doctrine, and redundancy cost time and metal. One week brought a crisis that would be told and retold on the shop floor for years. An early morning strike somewhere across the channel had wet the newspapers with sketches of blown cities. That evening, a shipment of hardened steel, ears of alloy destined for the accessory gearbox, sat on a loading dock when an air raid forced trains to be halted in a way that delayed dispatch. The next morning, a morning shift incoming found that the pallet of steel had been stacked under a leaking roof overnight. Rain had pooled through a seam in the tarp. Moisture had done its quiet, corrosive work. By midday, a run of gear sets processed from that batch began to show surface pitting that would have been invisible to casual inspection, but deadly in high contact stress. Walters's team caught some of it. A newly instituted in-process inspection had a trained eye for surface anomalies and quarantined the first few suspect gears. But a handful had already been pressed into assembly before the defect was recognized. It took only a few days for a pattern to emerge in the test cell logs, a spiking of fine particle debris, an uptick in bearing temperatures 3 hours into a run. The engineers traced it back through paperwork, shipping manifests, and finally to that rain-soaked pallet. The repair was a brutal mixture of logistics and human labor. Hundreds of parts were scrapped. Rework stations filled with boxes of gear sets sent back to be polished, rehardened, or in many cases melted down. Men worked through night shifts, faces lined with oil and the thin glaze that comes from watching metal go wrong and right. The foundry manager, who had been an invaluable steward of sand and flame, stood on the loading dock under an indifferent drizzle and said softly to nobody in particular, "We will not let the rain become the enemy." It was less a claim than a vow. There were casualties, not only the financial kind. A fitter named Joe, known for his swift hands, had been on a ladder when an aftershock from an explosion at a nearby freight depot sent a shower of rusted metal across the yard. He came down with a broken wrist that put him out of commission for weeks. Sam Keene, who had returned early from convalescence, suffered a setback when a pitted bearing failed during a late-night run. He caught his hand between a brace and a bench and left with stitches that reminded him of the price of miscalculation. The nurse's station recorded the smaller wounds, backs tightened by overtime, eyes reddened by constant sparks, the slow erosion of sleep. Those personal pains were folded into communal memory. Men and women stitched each other's uniforms, distributed ration coupons, smuggled a little extra bread for those with hungrier children. The factory's social bonds, small gestures, the knowing looks across an assembly, came to mean as much as technical success. When productivity metrics rose, it was the moral economy that made people sustain the pace without burnout. When they fell, people felt the drop not as a failure of a ledger, but as a diminution of collective trust. Amid this churn, a narrower technical breakthrough began as a series of almost invisible experiments. It had to do with cooling, yes, but also with the way heat communicated through housings and the way oil carried heat away from critical points. An engineer with the quiet authority of long practice, an older man from the metallurgical wing who preferred notation to rhetoric, began to suspect that the factory's accepted approach to baffling caused turbulent eddies in certain operating angles, and that those eddies corresponded to the times and regimes where assemblies first showed localized overheating. He sketched an alteration, a slight recontouring of the baffle that would smooth the airflow and push oil along a more laminar path across the hottest faces. The idea had been proposed before in the literature, in different terms, and often dismissed as a marginal gain not worth the disruption. In a production environment, a small recontour could mean hundreds of modified tools. The decision to try it had to be carefully staged. Walter and the chief machinist chose a single production run as a test bed. One bench would try the new baffle hardware, another would keep the old. Engineers instrumented both closely, adding additional thermocouples and an inline oil thermometer so they could chart not only maximum temperatures but the gradient of heat change across time. The first run with the new baffle was almost banal in its inception. A girl from the assembly line, young, decisive, with a knack for reading tolerances, installed the first modified part with a professional indifference that hid the novelty of the experiment. They started the engine, watched the numbers, and jotted down the curves. Over the first 50 minutes, there was nothing dramatic. At the hour mark, the test cell's instruments showed a subtle difference in temperature stabilization. At 2 hours, the trends pointed in a direction the team had hoped for but dared not yet celebrate. The modified assembly ran cooler by a narrow but consistent margin. Vibration readings held steady. It would have been easy to ignore the gain. Statistical noise can make miracles seem like bad data. But the plant had learned to value trends. With more runs and more data, the engineers gained conviction. The smaller temperature gradient meant seals lasted longer. Seals lost less oil. Fewer oil losses meant fewer surprises in other systems. The change per assembly seemed tiny. Multiplied across thousands of planes, the effect promised weeks of improved reliability for air crews and fewer forced landings. The baffle redesign did not stand alone. A cascade of supporting adjustments, slight changes in oil viscosity specification, a repositioning of an inspection point, and a refinement in the machining sequence that removed a burr that had been triggering early wear, created a package of modifications that, together, moved the needle. The plant instituted a formal policy. When a suite of small modifications consistently reduced known failure modes, it became part of the packaging that would ship with the assembly instructions. This was the heart of the lesson. Breakthroughs rarely arrived as single luminous flashes. They arrived as convergences of small choices, each with their own human story. Ruth's bearing finish, the draftsman's fillet radius, the foundry's gating tweak, the baffle contour. Each contributed a thread to a tapestry that, once fully woven, could hold under fire. Then came the harder work, replication under scale and under duress. New shifts learned the new ways. Tooling was revised.
Quality assurance changed from a policing function to a coaching one. The plant developed a rotation schedule so that the people who knew the subtleties trained the new arrivals on the machines, taking the load off the engineers, who had been pulled between design and production. Acceptance runs were multiplied. Where once an engine might be run in a single pattern, now the plant ran arrays of conditions: cold starts, extended high-power runs, rapid throttling, so they could catch marginal behaviors early. And the auditors came. Procurement officials and military liaisons walked through, their eyes trained to look for variance and their clipboards ready to quantify compliance. Wins were carefully recorded. Process changes were codified into manuals and sent up the chain. There was satisfaction in that. Proof that an idea born on a bench had made it into the institutional knowledge of a wartime machine. There was also the sober recognition that each step toward standardization reduced the improvisatory creativity that had saved them in early months.
Standardization conferred reliability at scale, but also froze solutions that might, in peacetime, be improved upon further. Once the line steadied, the plant's output began to shift weather patterns in the theater of war. P-47s, once scarce in theater, were now arriving in waves. Pilots who relied on the Thunderbolt wrote in more confident tones about meeting enemy formations and returning home with damage that, in earlier months, would have meant total loss. Letters from squadron leaders circulated on the shop floor were short and practical. "Thanks for reliability. Your work saves men." Those notes were not boastful. They were accountability manifested as appreciation. Operational montages, always careful to avoid sensationalizing human suffering, tell the outcome in human terms. Crews who had been forced to land behind lines because of engine failure were replaced with teams who, after a dozen sorties, reported less frequent in-flight mechanical loss. The Thunderbolt's ruggedness, paired with improved engine behavior, meant more effective bomber escorts and more resilient ground attack missions. The log entries of one pilot, clipped in Walter's office and written in a hand that tilted downward from fatigue, read, "20th sortie. Returned with heavy flak. Engine held. Thank you to the folks who put it together." Those few lines traveled like balm to the plant. But with operational success came more complicated consequences. Greater numbers of reliable fighters meant more sorties, more aggressive mission planning, and more destruction from the air. The same engine that enabled a pilot to return home also enabled deeper strikes into urban areas and longer, more persistent campaigns. On the factory floor, men and women began to reckon openly with this duality. Miguel, in a long entry penned after a train ride to a blackout town, wrote, "I made something that keeps someone alive and also gives someone a way to break a wall down 1,000 miles away. How do you carry both? I don't have the math." In small groups, workers discuss the ethics in the way that people discuss weather: practical, immediate, and often unresolved. A production foreman would say during a break, "We make things, the world does the rest." And the statement would be followed by a silence more complicated than assent. A young woman from the subassembly line would reply that if they could make the parts safer for pilots, then they ought to. The conversations were not theoretical. They were embodied negotiations of conscience. Public relations, too, tried to reconcile the story. Propaganda and morale offices framed the factory's output as a national achievement. Photographs showed smiling workers next to row upon row of finished fuselages, bright paint, and polished prop hubs. Those images were true but partial. They concealed the nights of sickness, the fatigue lined around eyes, and the occasional moral vertigo when a stickered crate left the dock bound for a front where maps grew redder by the month. Despite these tensions, the plant's work continued and intensified. Women moved into supervisory roles. Older veterans of the bench moved into training positions. The payroll expanded, and with it the social geography of the town.
Cafes filled at odd hours. The radio in the break room kept time with speeches and each news bulletin. The factory accumulated icons. A plaque for a group of women who had formed an impromptu repair team that worked a night through a bombing warning to keep a run going. A hand-lettered sign near the lathe that read, simply, "Mind the clearance." The plant's role in the broader industrial mobilization became more visible. Other plants adopted their baffle contours and bearing finishes. Engineers from other firms visited, notebooks in hand, to learn the practicalities of process that had been scrawled in the margins of the plant's working manuals. Industrial cross-pollination accelerated improvements beyond the Thunderbolt, seeding lessons into other aircraft and even naval engines. But with the spread of knowledge came an institutional flattening. What had been a localized virtue of improvisation became part of an industrial grammar. Efficient, repeatable, prosaic. And then, as if to test whether the plant's heat-tempered processes could survive the worst, fate threw a sequence of events at them that threatened to undo months of careful work. A regional blackout, caused by enemy action on a transmission substation, plunged the plant into intermittent power. Backup generators spun up, but the flux stressed heat treatment cycles. Ovens, once steady in their gradients, experienced cold pockets that altered metallurgical outcomes. For a few long days and nights, the plant operated on the margins, triaging production and prioritizing the most critical assemblies for the limited ovens. There was no drama in the moment, only a steady-minded triage and an inventory reshuffle. The lessons learned there would become another set of institutional practices. The plant prepared alternate oven schedules in advance and built a matrix that prioritized parts by their criticality to flight safety. When the blackout resolved and the oven stabilized, the plant went through a rigorous verification campaign. Rerunning older assemblies, sampling the fielded parts, and cross-referencing with test cell runs required more labor, but protected against the risk of an unseen, slow-burn failure. Those who had advocated for in-process inspection were vindicated. The plant recorded fewer catastrophic surprises in the months after, and the data backed the decision to invest time in such monitoring. By then, the Thunderbolts were moving out in production convoys that had the air of an exodus.
The plant's shipping yard was an orchestrated choreography of crated engines, packed instruments, and teams who had learned how to secure delicate assemblies for transit across a war-scarred logistical network. Sometimes, shipments were rerouted to avoid high-risk trains. Sometimes, they moved at night. One convoy left beneath a sky lit by distant flares, engines humming in their cratings like captive animals. Workers who had spent months shaping these machines watched them go with complex emotions, pride, relief, and a faint, persistent dread. Operational reports that followed were both gratifying and sobering. Pilots praised the plane's ability to take damage. Squadrons reported more effective ground attack sorties. But reports, even when they were succinct and grateful, sometimes included moments of human cost that could not be dismissed. A squadron report might mention successful suppression of an enemy position and, in a footnote, note civilian displacements or collateral damage. The plant's people read these reports with the same practical eyes used in the assembly shop, seeing their work in a wider field of consequences. As the war turned and the skies quieted, the plant moved into a different phase. The urgency that had been the plant's oxygen loosened. Men who had been drafted into the workforce left for occupation duties or civilian life. Women who had riveted and aligned left or stayed, some preferring the work's camaraderie and steadier pay. The machinery of production was repurposed, refitted, or parked. The test cells that had once coughed and roared were turned down. Hushed celebrations and small private commemorations took the place of the relentless cadence of wartime runs. The transition was not clean. For many, the return to normal felt like the softening at the edges of identity. Walter found his hands less steady when the pressure to deliver was gone.
Ruth took to teaching machining techniques at the local vocational school, translating the improvisations of war into curricula for peacetime industry. Miguel returned to his father's small shop, carrying with him the taste of industrial life and the tradable skill that would offer a bridge back into civilian work. Sam, who had borne scars both visible and invisible, kept one hand in light engineering. He preferred the quiet of precision work to the noisy confidence of the assembly line. Memory collected itself in objects. A cracked piston, removed from a test stand and kept as a ledger of what had been surviving and what had failed, sat in a glass case in the plant's lobby. A plaque listed the names of those who had worked through raids and through the darkest nights, not as a tablature of heroics, but as an inventory of contribution. Men and women would come and stand before these artifacts and trace their own hands' movement across the memory of the plant.
Museums, years later, would display entire engines, polished and exhibited with placards telling stories that tried to be faithful to both industrial technicality and human struggle. The engineering lessons did not vanish. The plant's process improvements filtered into post-war aviation, into the nascent world of turboprops and, soon enough, jets. The ethos of toleration, of designing for resilience instead of brittle perfection, would inform the next generation of aircraft designers. A few of the plant's engineers moved into aeronautical firms that turned their attention to jet engines, bringing with them the knowledge of metals, heat, and the humbling lesson that every design lives in a messy world that will always test theory against weather, supply, and human fallibility. The moral reckonings persisted. Some of the workers returned to homes where they were thanked and yet remained ambivalent. Restoration of peacetime life required a reckoning with what had been built and what those machines had enabled. Over long nights, retired workers met in clubs and cafes, and their conversations traced the arc of engineering pride to an ethical unease. They did not reach consensus. They recognized the ambivalence as a kind of grieving for a world that had made them both skilled and complicit in an industry of destruction and defense. In time, plaques were installed, and museums curated exhibits. Visitors pressed faces to glass and read the dry captions about horsepower, compression ratios, and production totals. The machines looked noble. They also looked like artifacts that carried a history, some proud, some painful. Children asked about the violence of war and were told, in careful words, that technology is neither virtue nor vice in itself, but a tool that magnifies human intent. Teachers use the artifacts to trace lessons about responsibility and the price paid by those who make instruments of conflict. Years later, a small group from the old plant, Walter among them, toured a National Museum exhibit. They stood by a Thunderbolt engine, now polished and presented with reverence. Walter ran a finger along a familiar flange and said softly, "We welded what we had to with what we learned." Someone nearby, one of the women who had worked the rivet guns, added, "We kept a lot of people in the sky, and a lot of people were kept out of sleep." They both laughed, briefly and without mirth, an acknowledgement of the paradox. The last chapter of the plant story is not a tidy moral, it is a human one. The building that had roared like thunder was gradually demolished in places, retasked in others. New industries occupied parts of the space, and the old test cells were sealed. In the quiet corners, artifacts persisted. An oil-stained logbook with a dozen running entries from a night in November. A coffee-stained sketch of a fillet radius with penciled notes. A coffee mug cracked at the handle but labeled in block letters with a name. A small, ordinary relic of extraordinary nights. There were formal ceremonies, too. A plaque commemorated those who had worked the lines. A smaller one recognized those who had been injured. Leaders in the community gave speeches that tried to balance gratitude with remembrance. In a whispered line at the end of a dedication, a speaker, mindful of the mixed legacy, said, "We remember skill, we remember sacrifice, and we remember responsibility." The line landed among the crowd like a benediction. The final scenes in this account happen in two small converging gestures. In the first, an old machinist returns to the site of his youth with his granddaughter. He brings her, carefully, to the case that holds the cracked piston. She peers, curious, at the patina and the scarred metal. He tells her, in a voice tempered by decades, about the late night when they pushed an engine past the point they thought possible and learned, as a group, how to make small changes matter. She asks a simple question. Did it make you proud? He considers the question like a man weighing coffee for the first time, and then answers, yes, and a little sorry, both at once. It is a heavy answer, but it is honest. In the second gesture, an exhibit curator in a regional museum writes a small note that will accompany a donated assembly manual. It will read, in a tone measured and factual, that the narrative in this film stitches together experiences from multiple wartime factories. And, while it honors the ingenuity and hard work of those who built aircraft, it acknowledges that the description of constant bombing around a singular plant is a composite drawn from many accounts. The curator hopes the note will help future generations hold two truths at once: that technical achievement can protect lives, and that it can also enable violence that leaves scars on cities and people. The story ends where the work once did, with a piece of metal, a record in an oil-stained notebook, and the faces of those who remember. Machines, like languages, carry the imprint of the hands that shaped them. The P-47 Thunderbolt, its name conjuring thunder in flight, was more than the sum of rivets and pistons. It was a product of people who argued with metal and, in arguing, learned humility. Outside, in the long hush after the war, the plant that had once thrummed with urgency kept a quieter rhythm. The cranes moved in sunlight. The test cells gathered dust and memory. The story stayed, handed down in diaries, in the pause of a machinist when he tightened a bolt, and in the voice of the woman who taught apprentices the fillet radius that would still save lives decades after the conflict ended. If the tale has a moral conclusion, it is not a single sentence. It is a set of tensions to hold. That human ingenuity can make machines that save. That the same ingenuity can also amplify harm. And that the dignity of work, of listening to metal, of teaching others how to listen, remains a fragile, essential counterweight to the forces those machines set in motion. When the granddaughter left the museum that afternoon, she carried with her the smell of old oil and a story she would later recite with the flat confidence of memory. The old machinist watched her go and thought, as he often did, of the men and women who had come through that plant, of nights he could not forget, of the quiet repairs made at dawn, of the places where things had failed and where they had been made to work again. He folded these recollections like maps into his pockets, and, for the rest of his days, when he saw a plane cut a clean line across the sky, he felt both a small pride and a small sorrow. This narrative has tried to take you into that room, the iron and oil, the test cells light, the hands that learned by doing. It has tried to be honest about what was achieved and careful about what those achievements enabled. The factory, in our composite telling, was a crucible, a place of craft and scale, of failures and incremental miracles, of moral reckoning and technical legacy. If this story moved you, please like and subscribe for more deep dives into hidden industrial histories, and consider visiting your local aviation museum or archive to see these machines and documents in person. There you can touch a catalog spine, read a logbook, and meet the material traces of the people who made history with their hands.